Yep.
So as the title shows, I would like to talk about the inverse dynamics control of underactuated robots, but I would like to really go into the details of some inverse dynamics control things, and there will be a lot of equations. Actually, I don't like it usually, but I think this topic cannot, or it's very hard to do without equations. So there will be a lot, and it will be a bit technical, but the first part when I'm talking about inverse dynamics, and please, so please ask if something is not understandable, or please tell me if it's already studied from other sources. So let's begin with a small introduction of my country. So I'm sitting in Hungary right now, in the not the middle of Europe, maybe it's a little bit Eastern Europe. And you may know Hungary from the famous football player, Ferenc Puskás. I don't know how you're familiar with him or not, but he was very famous, and his team was also very successful in the middle of the 19th century. And maybe another thing which could be famous in Hungary is the so-called solfege, or movable solfege, when you say do, re, mi, fa, sol, la, ti, do. I don't know if you know this, but this is also invented by a Hungarian guy, and his name is Kodály Zoltán, and as I know, it's well known worldwide. And one last thing about Hungary is the dynamo, which was also invented in Hungary by Arne Jedlik more than 100 years ago. Yes, so we are here now, and here we have a capital called Budapest, and in Budapest there is a university of which the main profile is engineering, but it also maintains economics studies, and it's quite old university. Actually, it was the first university in the technical field in the whole world, they say. So it was founded in 1782. And I'm from the Faculty of Mechanical Engineering, and there are some other faculties. So let's go into the topic. And the first thing what I would like to talk about is the dynamic description of robots quickly, and then I will talk about some control aspects of some of the conventional robots, and then I would like to talk about some more special robots which are underactuated, and I would like to talk about kinematic redundancy. So these are some special things, and then some applications. So let's go into the details of dynamic equations of robots. So the idea is that if I have a robot, or if I'm a robot, I would like to know what happens if I'm activating my motors or actuators. In other words, it's like in the case of children when they are learning how to move their body parts. So they just try to move or activate their muscles, and they learn that some movement will occur. So this is the same in robots, but in case of robots, the model is there, and this is the point. So if we have a model, then we can predict the motion if we know the activated motors and actuators. And I hope everybody knows here the Lagrange equation of the second kind. There is the kinetic energy and potential function. So it's usually taught in vibrations course. And what you obtain by using these equations is a function of the coordinates, the generalized velocities and generalized accelerations, denoted by Q. And there are, if we are talking about robots, there are usually some control inputs U, and sometimes it's not typical. Sometimes the equation depends on time, but it's not typical for robots, so we just drop it. So you will obtain some function, which is the equation of motion basically, which equals to 0. And in case of cellular robots, we can split this function into different parts. So if we collect the coefficients of the accelerations, you will obtain the mass matrix, which always depends on the coordinates. It cannot depend, for example, on velocities. It's not possible in case of mechanical systems. And you can also collect the coefficients of the control inputs U, and then you will obtain something which is usually called as control input matrix. And then there will be some kind of rest terms in the equation, and we will in the future, in this presentation, we will denote it by small c, and this is the rest. Okay, so finally you can, so if you carry out this calculation given by the Lagrange equation of motion of the second kind, you will end up this general form, which is applicable for almost all robots. So there is mass matrix times acceleration plus some other terms, depends on velocity and some other things. And finally, on the right-hand side, there is the control input, and there is the control input matrix. And here I show the dependencies. So, for example, mass matrix depends on Q, but now we memorize it and we don't want to see it anymore because it's too complicated. So let's use this notation without the dependencies. And is my cursor visible?
Mm.
Okay, that's good.
I see it well.
That's good. So let's take some very simple example. Let's say that we have a robot which is a driven physical pendulum, so it's just hanging down from the ceiling, and we have one torque applied here which can modify the angle of this pendulum. So if we want to collect everything, what's important, so we can say that the generalized coordinate is the theta angle, and we have control input, a single control input, which is the tau torque here. And then if we apply the Lagrange equation of the second kind, then we will have this nice second order ordinary differential equation. Right hand side you can see there is the torque, this is the acceleration, the angular acceleration, and here also we see the gravitational, this is the torque actually exerted by the gravitational force. And if you do this splitting, so you can collect the coefficient of the acceleration, which is the mass matrix, but in this case, this is a 1 degree of freedom system, so we have a one-dimensional Q. So the mass matrix is actually a scalar, so 1 by 1 matrix. And similarly, the control input H is also a matrix, which is actually a scalar, so 1 by 1 matrix. And we have some other terms in which the gravitational force appears. And let's do it for multiple degrees of freedom, just to see what happens if we have a not single degree of freedom, but some little bit more complicated. And this will be the card pole model, which we will use in the further part of the presentation. So the card pole model consists of a particle or rigid mass which moves on a horizontal constraint or horizontal rail, let's say. And there is another part which is a physical pendulum attached to the cart, and it's called pole. So this is the reason for calling it card pole model. So it is 2 degrees of freedom. We have 2 coordinates, and we also have 2 control inputs. So this system is fully actuated because I have as many control inputs, as many degrees of freedom. So everything is nice and easy. And if we apply the Lagrange equation of the second kind for this 2-dimensional or 2 degree of freedom problem, then I will obtain 2 second order differential equations. And of course, the mass matrix will be 2 by 2, control input matrix will be 2 by 2, and the rest terms, including gravity and some Coriolis forces and everything else, is also a 2-dimensional vector. So in the nutshell, this is what I would like to say about the dynamic equations of robots. So this is the most important equation here. So this form is always possible to set up. And then before we go into the details of the control of robots, we need to talk about inverse kinematics. So what's the main problem here? So if I have a robot, usually the task is to reach an object or move an object in a prescribed path. So from the point of view of this small robot, the task is to calculate the joint angles, for example, the shoulder joint and elbow joint, in order to reach that apple. So that's the big question for this small robot. And if we go back to our examples, we can again reformulate the question. So the first thing is the forward kinematics, which means that if I know the joint angles, or if I know my generalized coordinates, like theta of time here, then I am able to calculate the position of the tool center point of the robot. If I go back here, the tool center point is obviously the hand of this small robot, and if he wants to catch the apple, then the tool center point location should be identical with the location of the apple. So this is the same here. And if I'm calculating the tool center point location based on the already known coordinates or joint angles, it's called forward kinematics. But usually the opposite is done in case of robots. So there is a trajectory, which is the so-called desired trajectory or desired tool center point position, which does not exist in the reality. So this is what we want to do or achieve. So it just exists in our mind. So that's why there's a ghost here, because it's not existing in the real physical world. We just imagine a trajectory of the desired position of the tool center point. And the task is to calculate the corresponding joint angles. So TCP desired is given, and then I am able to calculate the corresponding angle, which can be handled as a desired joint angle, let's say. And the tool center point is usually a time location, is usually a function of time, an explicit function of time. And then I would like to somehow obtain the joint angle. So let's see another example where it is a little bit more visible. So let's go back to this 2 degree of freedom robot. And here the tool center point location is really a location in the X and Y coordinate system. So we are in a planar case. And tool center point X and Y coordinate is specified in the time, which means that this point is moving in the plane in time. And I am also able to calculate the end point of the robot, the tool center point, based on the coordinates. So if I know the X coordinate and the theta angle, then I am able to say where is the tool center point. And this equation must be solved. So the tool center point location is given by X and Y. So this whole equation must be solved for theta and X. And now this solution is very simple. We can have a closed form result, but in general it is not that easy. But so you can read in the books about this. I will show some literature at the end. So this the main message is that in case of inverse kinematics, the trajectory of the tool center point is given, and I would like to calculate the corresponding joint angles or generalized coordinates, which are called desired joint angles. And we will use in the further control these desired joint angles. So let's memorize this. And I would like to speak about 2 different kinds of control strategies. I think the first one was mentioned as a distributed joint control, and the second one, which I call inverse dynamics control, can be handled as a Moritz, how did we call it? Which is not distributed, the centralized control strategy, or
Centralized control. Yeah.
Okay, so yeah, so the second one can be related to the centralized control strategy. So in case of the decentralized one, let's see what happens. So again, let's go back to our very simple example where we already know that we have some desired joint angles, and the idea is to eliminate the difference between the real position of the robot and the desired position of the tool center point. So the question is how to eliminate this. And that is a very simple solution. So we imagine that there is a spring and a damper between the two. And from our vibration knowledge, we know that the tool center point will be converge to the desired tool center point, or we will see it later if it converges or not. We feel with our engineering intuition that it will just pull close to the TCP desired. And it can be formulated in a simple equation. So the tau, which is here, which is the torque exerted by the actuator up here in the joint, the torque is equal to gain, which is called proportional gain, because this is proportional to the position error or the angular error of this bar. And also there's another term which is proportional to the velocity error, and this is called differential gain here. And if I use this equation, we can recognize that this is very similar to the equations which are appearing in vibration course. So basically this P and D play the role of the spring and the damper. So we feel that it might work. And let's check it out if it really works. So I take again the equation of motion of this very simple system. So it was already shown at the beginning. And at the right hand side, there is the control torque. And let's replace the control torque with this control law here. So I just substitute P and D here instead of tau. So I just put this whole thing into the right hand side of the equation. And let's check what happens after a very long time. So we know that if there is a spring and damper, the motion will settle down and everything will be in a static position. So if we wait long enough, there will not be any acceleration and there will not be any velocity. And let's assume that the desired position is a steady position. So I just say 30 degrees or 60 degrees or something, and it's not moving in time. So we substitute these things into the equation of motion together with the control law here on the right hand side. And these terms, which are velocity or acceleration dependent, they will be zero, and then the middle part will remain. So this is the equation for the static equilibrium, basically. And here we will see that the positioning error, the desired minus the real angular position of this bar, will be equal to something which depends on gravity. And also the proportional gain appears here. But the main thing is that it is definitely not zero. So if the desired angle is, I don't know, 60 degrees again, then there will be something here which is not zero. So definitely there will be some positioning error, which is a problem. But we can actually notice that if the proportional gain is infinitely large, then this term will be zero. So if I tune P to infinitely large, then actually the black one will move to the green one. So the real position of the robot will be identical with the desired one. But it's not possible in reality. So P cannot be an infinitely large number. Let's see the same thing in case of the 2 degree of freedom example. So I can do something similar. I can apply a P term for the X position error, which is the position error of this mass here, the cart, and another P for the angular error. And that's why we can call it distributed, because this controller calculates the force, which is up here, and the force deals only with the positioning error in X direction, and the tau deals with the angular error only, and it doesn't have any information on the dynamics of the whole system. And we see that there are a lot of parameters to tune, but this is not the biggest problem. Yes, and this is called trajectory tracking. So in the outline, it was called trajectory tracking control. So trajectory tracking means that there is a desired trajectory, sorry, with the green one, and we would like to follow or track this motion. So we would like to achieve, we would like to design a controller with which the real trajectory, the black one, converges to the desired one. which is the green one. So here you see that the error between the two is actually 0. So we would like to achieve this. But in case of this distributed control, there are some problems. So as we have seen before, the positioning error, depending on the situation, is usually not 0. So because of gravity, there is always positioning error. And because of the digital effects, we cannot choose infinitely large gains. And also, actuator limitations are the reason for not choosing infinitely large gains. So we have to do something else. One solution which is usually used in robotics is to apply a PID controller, in which the idea is that the error is integrated. So there is a further term here which integrates the error, but the dynamic analysis analyzes a little bit more problematic than the simple PD controller. And so it usually works with conventional robots, but in underactuated robots, it's definitely not the way of solution. So the better thing what we do is to apply some kind of inverse dynamics control, which applies the information about the model of the system. So let's go into the details of the inverse dynamics controller. So the idea is to use the model in the control. So let's go back to the equation of motion of this very simple example. Again, there is the mass moment of inertia times the angular acceleration, some gravitational effects here, and on the right-hand side there is the control torque. And this equation actually allows us to calculate the motion if the control torque is given. So if I put here, let's say 10 newtons, I will be able to calculate the time history of theta. So it will turn around or it will oscillate. So something will happen due to the torque which I apply here. And it is called forward dynamics when the torque is given and the motion is calculated. But we can use only also the opposite purpose. So we can use the equation for the opposite purpose. So we just switch the two sides and we say that the motion is given. So the theta angle is given in time and we call it desired joint angle. And if it is given by using time differentiation, we can recognize that the acceleration for the same joint angle is also given. So it means in this case that the angular acceleration of this pendulum is given. So everything is given in the right hand side. We know the motion, and then we are able to calculate the torque which must be applied here in order to achieve the prescribed or desired motion. And we call this technique as inverse dynamics. So basically we use again the equation of motion, but the unknowns in the equations are different. So here the forces or torques are unknown when we are talking about inverse dynamics. And it is I know how famous it is, but some people always say that force or motion. So you can specify force and then you can calculate the motion, or you can specify the motion and then you will be able to calculate the appropriate torques or forces. So this is a very important message, I think. And let's check out this example in a little bit more detail. So for example, I'm thinking about only the angular acceleration which is specified, but let's say that it's in hanging down position, vertical position, then the gravitational term doesn't have any effect. And basically I can calculate the torque which is needed to accelerate the pendulum in the certain magnitude. Or I can change the situation. So let's say everything is in steady position, so there is no acceleration, but the desired angular position of the pendulum is given here in the equation of motion. So I cancel out the acceleration terms. I just deal with the gravitational force or the torque which is exerted by the gravitation, and then I will be able to calculate the corresponding torque which keeps the pendulum in this static position with desired angle. So it's possible by just using the equation of motion. So it seems good. Let's try to apply it in general. So we take the equation of motion, the general form, our equation of motion. Again, I try to show the dependencies for a while, because it will be important just now. So this is the equation of motion, and this is what we said before. So if the motion is specified, then I am able to calculate the control input. I'm just going back for a while. So here I just flip the equation. So tau is just put on the left-hand side, and we say that this is the unknown. But in general, there is this so-called control input matrix. But it is, for fully actuated robot, it is an invertible matrix. So I can just invert it, and then U is possible to be computed. And then here there are the prescribed motion or desired motion on the right-hand side. So it's very simple, actually. And now we get rid of this dependency. So this is the same equation, but I don't show which matrix depends on which parameter. So it's just the very simple form. So U is simple to calculate if the motion of the system is specified. But I have changed one thing here. I don't know if someone recognizes it. So instead of acceleration, I put here a vector which is called V. And this V is basically so-called auxiliary input or synthetic input, or they just say this is some kind of new input of the system. And obviously, if V is equal to the desired acceleration of the system, everything will be nice. But then the modeling errors will not be handled. So modeling errors means that in reality, I'm not able to measure the mass of the robot exactly. So there will be always some error in the mass matrix. I'm not able to determine the behavior of my actuator. So age will be not the real one. So there are always errors, and actually there are always measurement errors of the real coordinates. So there are always errors. So what is done in reality is to choose V as the acceleration, the desired acceleration of the joint angles, which can be obtained from the inverse kinematics calculation, which we have seen earlier. And we also include these kind of PD terms, which are responsible for the positioning error compensation and also for the velocity error compensation. So D behaves like really a dashpot or damper. So it helps to get rid of oscillations, and P provides the convergence to the desired position. So if Q desired minus Q is 0, then everything is all right. And let's check this out. So these two equations are basically forms the control law, but let's check it out if it works. So I take again the equation of motion. So these are the these two are the same equations, but now I get rid of dependencies. So this is our equation of motion. And instead of U, I am just putting here instead of U this expression. So as we said, U is calculated as H inverse times this bracket. So let's put this here. Okay, so it's H inverse times the mass matrix times the auxiliary input plus C. And we also put here the auxiliary input, which is defined in this equation. So instead of V, we just say that, okay, this is Q desired, Q double dot desired, and the PD terms. And let's see what happens. So here we see that H cancels out because H times H inverse is an identity matrix. We get this bit more simple equation, and then further we see that C cancels out and the mass matrix cancels out, and finally we achieve this equation, which is basically, we can recognize is that it's identical with the, so it shows us that the acceleration of the system will be identical with the auxiliary input which we have specified here. And this is called feedback linearization, which is always possible for fully actuated robots which are not in a strange situation. So in the case of normal robots or commercial robots or classical robots, it's always possible. And then we also introduced something new. This is the error defined as the difference between the desired and the real joint positions. So after we introduce this error and apply in this equation, we will see that we have a very nice equation for the error. It's usually called as error dynamics. And again, this is an equation which is, I hope, familiar from vibrations course. So everybody knows that this equation has a solution which converges to 0. So this is a stable equation in case of positive P and D, so positive definite matrices for P and D. So it really works. And as we see, there is no positioning error if we apply this kind of inverse dynamics control approach. And let's check this out for the 2 degree of freedom example. So here, the auxiliary input, which is defined here, is very simple. So this is the desired acceleration for the x and theta. And also there are some terms which are related to the error in x and theta direction and in the velocity error. So this is v, and we put it here into the equation of motion. So this is the general form. So we flip the equation and u is calculated. So this is the general form and everything is put here. So if I want to control this with inverse dynamics to control, these are the 2 equations what I have to maintain and nothing else. These further equations just shows that it really goes, the error really goes to 0. So it's stored in video. So later you can check these equations. Now I don't want to go into the details. The main thing is that finally you will end up this equation for each degree of freedom. So the error in x will go to 0 and the error in theta will definitely go to 0. And let's check this out in animations. So if I have the simple PD, what we have said at the beginning, and we were also referring this as a distributed control without the using of the model of the system, we will see that due to the gravity, there will be a positioning error between the green, the desired, and between the real, which is the red, position. But if I using inverse dynamics control, then the desired and the realized position will be identical theoretically. So if I know the model exactly, then this will happen. And now we see that this is a static position. The desired position is a static one, but it also works if the desired state is a moving thing. So in case of PD, the simple PD or distributed, we see that the moving of the desired state also causes some inaccuracies. So even here, the X position has a large error due to the motion, but inverse dynamics handles this too. So no problem with the moving desired states. So this is the animation for the card-pole model. And let's sum up what are the benefits of the inverse dynamics control. So it's very accurate, as we have seen, and it is easy to tune. So I would like to just go back a little bit. So it's not accidental that I were writing the same D for the both equations in X and theta, because here we see that the aerodynamics is identical for each degree of freedom or for each joint. So it doesn't make sense to choose different P and D. So the same P and D can be applied for every joint, and it's very simple to tune them. But there are also drawbacks for the inverse dynamics controller. So the model is complicated. We have to make an identification of the robot. So it's much more complicated to implement. And the other sad thing is that if I have a friction, Coulomb friction or viscous friction, it's very hard to measure. So very hard to set up the dynamic equations for the friction. So actually inverse dynamics does not help too much in the handling of the friction. So that's always an issue. And of course, if I have inaccuracies in my model, that will cause inaccuracies in the operation of the robot. So let's sum up where we are now. These things were applicable. So what we were talking about so far are applicable for let's say classical robots, but we can specify here what I mean on classical robots. So they are fixed on a rigid base, so they are fixed on the ground. They are serial robots, so there is always a joint and then a rigid link and then another joint and another rigid link, so they are connected to each other in a serial chain, and the joints are ideal. They are fully actuated, so there is a motor in each link, and they are not redundant. Later we will see what redundancy means. So this is the simplest case, but I think most of the robots are fit to this picture. And the things what we have seen so far are summarized in some very good books and maybe paper, but I think these are all books. Okay, so you can check these books out, and they are very useful if you want to understand these robotics control in more details. And from now we will move to some robots which are, let's say, not normal or not classical robots. We can say that these are extraordinary robots. So a lot of things can happen, and these robots. So in general, robots can be much more complicated than these industrial robots. So they can move around in our home. So domestic robots can move around in our living space. They can cooperate with people, but of course they must be very, let's say, safe. So they must not be dangerous. And this one thing what we can do is to make the robots soft. So this is why its course is very important. So soft robot means that it will not kill me if I make some error in the controller. So it is much safer than these kind of industrial robots. Actually, if we are using these industrial robots, people are not let to go in. So there is a fence here. People are not let here because you can really hurt yourself if you go there. Okay, so there are very interesting robots out there. Legged robots are very important. They walk on legs like humans, and there are some kind of hyper redundant robots, which means that there are a very huge number of degrees of freedom, and they can achieve some snake-like or worm-like motion. Actually, the sensory system can be very colorful. For example, I guess you were talking about whiskers, so they can touch the environment and they can make some decisions based on this information. There are also tensegrity robots or parallel robots. Parallel robots are very specific because the modeling approach what we have seen before is not applicable for them. So you have to do some multi-body dynamics work if you want to get the model of these robots. And robots which are hanging down from something are also quite special. So this is another word, and there is a huge literature then. And let's first talk about kinematic redundancy, and then we will go to the details of underactuation. And these are definitely not the simplest robots which have kinematic redundancy. So when we are talking about kinematic redundancy, maybe the human arm is the best example. So as we know, there are 7 degrees of freedom. Actually, you can try this and try to calculate your arm's degree of freedom. So the shoulder actually represents 3 different rotations. The elbow can be rotated along one axis. The forearm is able to rotate about its along y-axis, and the wrist has also 2 degrees of freedom further. So finally we end up with 7 degrees of freedom for each arm in the human. And this is kinematically redundant because if I have a task which tells me that I have to move my hand in a certain position and in a certain orientation, I just need actually 6 degrees of freedom, because rigid bodies can move in the space and they possess 6 degrees of freedom, but my arm has 1 more degree of freedom, so I will have 1 more degree of freedom, and I can do what I want to do with this extra degree of freedom. So human arm is very agile, and that's why the robots are very similar to the structure of human arm. Let's go to some other examples where it's much more understandable in the mathematical level. But before we detail the kinematic redundancy, let's go to the forward kinematics, which we were talking before actually. So forward kinematics means that I have information about the joint angles, and then I will be able to compute the end point or tool center point of the robot. And the opposite is the inverse kinetics, when the tool center point position is given, and I have to calculate the corresponding joint angles. And here we already see one problem, that there is more than one solution, even in this very simple case. So here the XY position of this black dot is defined, and then I can choose this configuration of the robot or the other configuration of the robot, and both will satisfy the task, which is to reach this XY point. And there is another problem, since sometimes the defined position cannot be reached by the robot, so it's actually too far from the robot's origin. And in this case, there is no mathematical solution, so you cannot choose any coordinates, any joint coordinates with which the robot will reach this black dot. So there are definitely some problems in the inverse kinematics. And you can also recognize here that the number of degree of freedom of the robot, which is 2 now, is equal to the number of the task. So we defined two things here, two positions, and this is not a kinematically redundant problem or robot, because the joint variables equal to the number of the task. But what happens if it is not true? In case of kinematic redundancy, like in the case of the human arm, you have more joint angles or joint coordinates which would be minimally necessary to achieve the task. So here again, the task is two-dimensional. I have to reach x, y, and I have to determine 3 joint angles. And this is the case of kinematic redundancy. So all in all, we can say we have more joints than necessary. And what is the thing of this? It means that I can have infinitely many different kind of solutions of the same problem. So here, this is the simplified, this is the animation of the model with the 3 degree of freedom. And these are the different colors mean that we have several solutions for the inverse kinematics. So the endpoint moves in the same trajectory, but the joint angles are very different in case of each color. So the same robot moves in a very different way in case of each color. So this means that we have kinematic redundancy. We can also see the whole thing in another geometric approach. So we are in the space of the 3 joint angles, Q1, Q2, and Q3. And when I'm trying to find the configuration of the robot, it means that I would like to find one certain point in this space, because one point in this space corresponds to a certain shape or configuration of this robot. And when I'm specifying the desired X position, it means that I will have one equation for Q1, Q2, and Q3, which means that I have a codimension 1 object in the 3-dimensional space, which is basically a surface. So actually it means that if I move any point in this surface, the X position of the endpoint will be correct. But I'm also specifying the Y position, the vertical position. It means another scalar equation, and this other scalar equation introduces another surface in the 3-dimensional space, and my point in the configuration space must move on both surfaces, which means that the intersection line or intersection curve is the place where I can move. And basically in the previous animation, we were moving on this intersection curve, and it means that the endpoint will remain in the desired X, Y position. And how can I choose the solution, my solution among the infinitely large number of possible solutions? We can introduce any equation what we want. this is an arbitrary equation. Let's say we say that Q3 is a certain number, and then it will introduce another surface in this three-dimensional space, and finally the intersection of the three surfaces will be one single point. So after introducing one extra equation, I will have a unique solution for my problem. So this is kinematic redundancy, and soon we will see why is that important in case of underactuated systems. So let's get some idea what is underactuated system. I guess you have already seen some things from Professor Moritz Scharff, but let's approach it from different direction. So this robot seems to be a fully actuated robot because, like a human, so we have muscles for each joint, and we can be handled as a fully actuated systems. Actually, we are over actuated because we have more muscles than joints. So we would think that we are fully actuated. But what happens when we jump or run, and what happens in the flying phase? It will soon turn out that, for example, we can exert any force on ourselves, and when you are jumping, you are not able to modify the path of your center of mass. It will move on a parabolic path. You can strengthen your you can bend your arm or extend your arm, but your center of mass will be definitely moving on a parabolic path, and you cannot do anything with it. And this is because that there are some degrees of freedom which cannot be directly actuated by any force or muscle. And it means that definitely there are some systems in which the number of control inputs is less than the degrees of freedom, and it happens almost everywhere in the real life. And in case of mathematical level, the problem is that if we take our equation, which was used in inverse dynamics control when we expressed the control torques by the inversion of the control input matrix, it will soon turn out that H is not a square matrix, which means that it has a higher number of rows than number of columns. So we are not calculate the inverse of this matrix in a normal way. So this is one thing which causes the problem. But there can be some other points of view to understand what's the problem here. So for example, let's consider this crane-like structure. It's a very difficult task to move the payload on the prescribed path, and actually this is why the operators of the cranes might have to practice a lot, because actually they have to learn the dynamics of the whole system. So if we want to take a closer look on some simplified model, we can say that we have 3 degrees of freedom. So 1 degree of freedom is for the cart, which is moving up here, and 2 further degrees of freedom are for the payload. So don't forget that here the cable length is varying in time, so we can make it shorter or longer. So we have all in all 3 degrees of freedom, but we only have 2 actuators. One moves the cart up here in horizontal direction, and there is another motor which changes the length of the rope, but nothing else. And actually the swinging motion of or oscillatory motion of the cable cannot be actuated directly. So this is why operators of the crane can learn a lot how to control this crane effectively. And if we want to control it by a computer, then we have to use some very clever controller. And let's see some animation of the same problem, but it's similar problem, but in 3 dimensions. So here there is a simple robot of which there is a so-called swinging unit which hangs down from a cable, and basically this is the unit which carries out the tasks of the robot. So it must follow the prescribed trajectory in a precise way. And what we can do is that we can move the position of the upper mounting point of the cable in X and Y direction, so in the horizontal plane. And furthermore, we can change the length of this main rope. So this is what we can do. And let's see if it's possible to follow this rectangular shaped path. I hope So, so do you hear the sound?
Oh.
So maybe the sound helps to I'll just tell what should we focus on. So the sound helps to feel that now there is no any underactuated control. We just we just project this square up to this plane, which is in the plane of the upper mounting point, and the robot is just following this rectangular shape and nothing else. So you can hear the motors. They just accelerate and decelerate in each side of this rectangle once, and nothing else is done. And you can see that there is a very high oscillation down there. So just once again. So acceleration, deceleration, acceleration, deceleration. And you see that it's very seriously oscillating. And now we apply some inverse dynamics approach, and you will hear the motors that along one side of the rectangle, it's twice or three times accelerate and brakes. So it's much more complicated motion. And you will see that the middle point of the swinging unit will move on a rectangular shaped path, and there will not be too much swinging motion. It starts every corner. Okay. And actually, this is done by just using the dynamic equations of the robot. This is some MATLAB computation or the animation related to the MATLAB computation. And here you clearly see that the upper point is not moving on the same rectangular shape. It's doing some loops and everything else. So it's given by the dynamic equations of the robot. And you can actually try this at home with some rope and some mass which is fixed on the end of the rope. So it's quite hard task to follow a shape with this system if we are controlling it by hand. Okay, let's see some other examples. We said that in everyday life, underactive systems occurs everywhere. So if you consider your hand and if you use it in a normal way, then one control torque or one control action is actually for bending the whole finger, but one muscle moves two joints in this case. And the other thing what we can normally do is to bend this joint here. So there are two independent control inputs, and these are, let's say, prohibited motion. So some people can do this. I can actually also do this, but it's not the normal operation of the finger, right? So finger is also, or the whole hand is also an underactive system, and this is the reason why it's very so it can easily adapt to the environment. So this is the same hand, and we can grasp any shape of object. And you see that it nicely fits there. Even we have a very strange shape, and that's why the robotic people tries to copy the operation of the human hand, because this is a really beautiful and efficient structure. And this is, as we said, underactuated. And this is again another typical problem. So aircrafts has 6 degrees of freedom since they are rigid bodies in the three-dimensional space, but we have actually 4 different control inputs which are independent from each other. So there is the rolling motion, which is exerted by this, I don't know exact the name, but these are some flips or what. But you can also use in the tail the same actuators, but this will cause the pitching motion of the airplane. And there is another one in the vertical wing here in the back of the airplane. This motion is called yaw. And furthermore, you have the thrust force, what you can modify with. So this is the gas. So this is the 4 different control actions what you can do, but the whole system is 6 degrees of freedom. So this is why the airplane is much more hard to learn to drive than a car, because in cars, that's another story. But in cars, the cars are not that underactuated like aircrafts. And we arrived to a very important thing, because if you have some soft robot or elastic robot, elasticity also introduces underactuations. For example, here, if the shaft is made of a flexible thing, and we know that everything is flexible in some extent, then basically this will form, in a simplified point of view, it will form a 2 degree of freedom system. So 1 degree of freedom is the angle of the motor, and there is a spring here, and the other degree of freedom is the angle of the inertia, which is driven by the motor. But we have only one input, which is the voltage or current of the motor, the electricity. So again, if you have flexibility anywhere in your robotic system, and if it is large enough, then you have to consider it, and you have to handle this in your underactuated control algorithm. So let's go into the details to underactuated robots. So at the beginning, I would like to say that it's a very huge area. So I will just show some basic things, and there will be a lot of further readings. So it's really a big word. So again, go back to our cart pole model, and as you see here, I removed the torque from here. So we can actuate the cart with this force, small f, and the theta angle cannot be actuated directly. And I intentionally say that it cannot be actuated directly because we can actually has an effect on this theta angle by just moving the cart up here. Okay, so we have some effect on it, but not a direct effect, let's say. And let's analyze what we can do with this in the simplest case. So here I say that we introduce something here. So we will define the task with this sigma function, which is nothing specific. It's like constraint for the coordinates, and this is an equation for. So this is actually equals to 0. So this equation says that xt should be equal to the desired x position. So one thing what I can do if I have just one actuator is to control the x position of the cart up here, but then I cannot have any effect on the swinging motion. So at the end, it will just hang down like a dead rigid body and nothing else. So if I'm controlling the x, I cannot do anything with the other degree of freedom. Or let's say that I'm trying to deal with the angle of the pole. You can easily check the equations or just simulate in your head that you will have a certain static angle if you have a constant acceleration of the cart in sideways direction. And then you can just use a triangle. So the vertical side of the triangle is the gravitational force, sorry, gravitational acceleration, and the horizontal side of the triangle is the vertical acceleration of this cart. So you can calculate how you need to accelerate your cart, and then you can compute the corresponding force. But you will see that it is not useful. So with the x coordinate, I cannot do anything. Okay, I can handle the angle of the pole, but I cannot do anything with the cart. It just accelerates sideways. So it shows that you have to choose what you want to do. So you have less actuators than degrees of freedom, and the number of things what you can do, or you can say the number or dimensions of the task is equal to the number of actuators. So here we have one actuator and only 1 degree of freedom can be actuated directly, and the other degree of freedom will do something what we don't know if we don't have the equation of motion. Sorry. And the other important message is that since the task is task has less dimensions than the degrees of freedom, underactuated systems are usually kinematically redundant. So this was the definition of kinematic redundancy. So the number of tasks is smaller than the degrees of freedom. And let's see some control algorithms. So of course we can carry out some more complicated control tasks. And we will see 3 different kind of controller concepts. And the first one is very simple, and if you have an underactuated system which is not that problematic, this is the first thing what you should try to apply. So let's again take the equation of motion of the robot. So mass matrix, acceleration, the rest, let's say rest vector, and the control inputs on the right hand side. And we also introduce an equation which is the servo constraint equation we have seen here. So here we define what is the task of the robot. The coordinates, for example, must be equal to the desired coordinates. So this is just an algebraic equation. But we don't like algebraic equations together with differential equations because it's mathematically problematic. So we would like to solve these two together, and then we hope that we can get the control inputs u. But if we want to do that, we have to solve together the dynamic equation and also the controls. Sorry, I just mute for a little. Can I do that?
Sure.
Okay. Sorry. Okay, so we don't like that we have algebraic equations and differential equations together, and we can get rid of the algebraic equation if we just apply some time differentiation of this algebraic equation. So after one time differentiation, because of the chain rule, q dot will appear here, and this is the Jacobian of the same function, sigma. And then there will be some terms which are explicitly time dependent. And then we can differentiate one more, this equation, and then the happy thing is that the acceleration will appear here. And this is very important. So now we have the dynamic equation, and we have the acceleration level constraint equation, and in both equations there is the acceleration of the coordinates as unknowns. And we would like to compute them, but that is the problem because u is also unknown, so our ultimate goal is to compute the control input u. And this term actually is responsible for the constraint forces which helps to maintain the servo constraint. So it has a theory in multiple dynamics. So if I have some constraints, there should be some constraint forces. And now the control input itself is the constraint force which helps us to maintain the constraint itself. And if we take these two equations, basically they can put into a hypermatrix form. So this line is representing the first equation, the dynamic equation. So m times q double dot plus minus h times u. There is a missing minus here. So h times u is put on the left hand side. So this should be minus h times u, which equals to minus c, which is put on the right hand side. And in the second equation, we have q sigma q times q double dot, which equals to these other terms put on the right hand side. So we can put this equation together, and we can solve it actually after inverting this hypermatrix. We can actually solve it for the acceleration of the system and also for the control inputs, and that's the important thing for us. But it will not work because of the inaccuracies in the system. And we can also recognize that there is no any PD term, but PD is always necessary even if we are using inverse dynamics control. So just like in case of Baumgarten stabilization, which is very well known in multibody dynamics, we say that instead of just dealing with the double time derivative of our constraint equation, so this is the same equation, we also use the first derivative multiplied with some number and also the zeros derivative, so the control equation, so constraint equation itself multiplied with some certain number, which can be handled as a gain parameter, like in the PD controller. So we use this equation and we will put this into this hypermatrix form, and then this provides the stable behavior of the constraint. So finally the robot will converge to the desired motion, and this will converge to 0. And let's just understand the idea. Why would we use this 2 alpha and beta here? So let's take a very simple example. So if I'm just going now to the multiple dynamics representation of this whole constraint thing. So if I have a rigid body and there is a constraint which tells us that xt must be equal to L, so this is the constraint equation here for this simple system. And then I am taking the first time derivative, which is x dot equals to 0 because L is constant, and the second time derivative, which tells us that x double dot is 0. We already see that in the acceleration level equation, we already lost the information about the length of this robot, about the length of this rod, which is a problem. But after we add these terms, so I have 2 alpha times the first derivative of the constraint equation, which is this, or this one, so 2 alpha times x dot plus beta squared times x minus L, sorry, a beta missing in the right-hand side. But we will see that this will be some equation of which the motion is the red one. So if I'm taking just this second derivative according to time of the constraint equation, the solution can be this blue one. So if there is some initial condition with a non-zero velocity, the solution can go to the infinity. But after I apply 2 alpha and beta square times the velocity and position, then the solution of the acceleration level constraint equation will be converging to the real position of x, right? Which is L. So let's see some applications of this whole formalism. We developed in our department some robot which hangs down from the ceiling, and the task of the robot is to move the swinging unit in the three-dimensional space of the indoor environment, like in the room or kitchen. And some other tools can be attached to this swinging unit, like a handlebar, which can help elderly people to stand up and walk in the flat, or it can be equipped with a gripper, or it can service some mobile vacuum cleaners or something like that. So it can also move a camera in the three-dimensional space. So the idea is to move this swinging unit in a controlled way in the three-dimensional space. And in a simplified model, which is a planar model, we can see that we have this robot here. These are the cables. This is a rigid body, the gray potato, let's say, and it has 4 actuators. So one actuator is the cable force in the main cable. There are 2 other cable forces in the 2 secondary cables here and here. And we have a thrust force exerted by a fan. The force is written here. So we have 4 actuators, and consequently we write up 4 constraint equations, or 4 servo constraint equations, which define the task of the robot. So for example, the first equation means that this 1/2 times x3 plus x4, this is actually the expression for the center point of the robot. And this must be equal to the desired x position. And this is the same equation in vertical direction. So the center point should maintain z elevation. And this equation is very similar. It's just maintaining the elevation of this P2 point. So the elevation between the swinging unit and this point should be equal to HC desired. This is just a number. And the last equation tells us that the difference of the elevation of the third and fourth point should be equal to some number. So we can also tune the angle of this swinging unit. So actually these are the control laws. And actually the degrees of freedom is much higher, so, or not much, but some kind of higher, because this is a three-dimensional object in the planar space. and we have which is 3 degrees of freedom and 2 degrees of freedom for this point. So at least this is 5 degrees of freedom. So yeah, it's definitely underactuated. And let's see some animations. So if the controller is not that clever, there will be a lot of oscillations of this cable connection point here. But on the right-hand side, you will see that if the controller is designed in a nice way, that then there is no any unnecessary oscillation. So it can really follow the trajectory which is prescribed. Okay, let's move to the next approach, which is based on direct discretization. So the first method was based on the Lagrange multiplier formalisms from multibody dynamics, and the next one will be based on direct discretization. Actually, this was suggested by a mathematician guy for us to try to apply this for underactuated systems. And let's first see what's backward and forward Euler discretization means. So let's say we have a differential equation, x dot equals to some function of x, and we have two choices. So x dot can be, so we are in digital world, so we would like to solve it by a computer. So t is not a continuous thing, t is just going step by step. So the approximation is x dot is possible with the value of x at ti and ti plus 1, or we can choose the other thing when we can take x at ti and ti minus 1. And the red one is the so-called backward, because we are here. So this is the time when we are evaluating the function and we reach back to some previous solution. And this is the so-called forward when we are going ahead. And so these are some complicated things, but it seems that it's not that. So actually, in case of forward, so the main thing is that in forward discretization, we can easily express the next value of the x when we are carrying out the time integration of this ordinary differential equation or numerical solution of this. So x in the next time step can be easily expressed. And this is the formula, what is in the figure. But in case of backward discretization, when we are reaching back here, the problem is that the new value of x is also in the function and also here. So we have to solve it for x ti, and this is usually a nonlinear algebraic equation set, which is kind of problematic. So it's harder to implement. But the benefit of using the backward scheme, the red one, is that it is much more stable. So if you check the stability diagram, it shows that there is a very small region for the forward scheme. So we have to choose this time step very carefully for this model equation. Otherwise, the solution will not real. It will be just some unstable solution which doesn't have any connection with our original differential equation. But in case of backward discretization, except this small area, I can choose my parameters from anywhere. So it is very stable and very convenient. We don't have to deal with the stability problems. And that's why this mathematician tells us that, told us that we should apply this for our problem. And what was our problem? Again, this is the same. So this is the dynamic equation where H is not invertible, but we would like to compute U. And this is the servo constraint equation in the acceleration level, extended by the Baumgarten term. So we already have seen this equation. And we would like to solve this equation set for Q double dot and U. And the idea is just to make a first order form. So we introduce some new variables. Instead of Q dot, we use Y. And we discretize it with the backward scheme. So instead of dot, I just say that it's Qi plus 1 minus Qi. And instead of Y dot, I just say the same. And the problem is that as we said before, we have to solve a very ugly nonlinear algebraic problem. So these are the unknowns in the system, the q, the velocity, and the control input in the upcoming time step. But actually, these terms also appear everywhere in the system. So also in the mass matrix and in the sigma. So it's full of unknowns, but it can be actually handled with some Newton-Raphson and other solvers, which is useful for nonlinear algebraic problems. So it actually works. And some publications can be also found here in this slide. The last one is a book. So it has a lot of details about underactuated systems. And let's go to the last one, which is the most theoretical approach to the control of underactuated systems. And actually, it would take at least 1 or 2 hours to explain it in details. So we will just again show some literature citations. And the main idea here is that this is our equation of motion, but as we said, H is not a square matrix, which can be also said that H is not a full rank matrix. So it is the rank of H is smaller than the degrees of freedom of the system or the number of coordinates, so it cannot be inverted. But we can reorganize our equations, and there can be a part of the system which is, let's say, actuated. So A means actuated. So this is a part of the dynamic equation which is fully actuated, but there are some other equations from which we can get rid of the control inputs on the right-hand side. So it represents that we have some degrees of freedom which are not actuated at all. So after reorganizing our equation like this, we can follow the idea of the partial feedback linearization. And it actually always works, but it's very, very complicated. Calculations are involved if we are applying this, but this is the last thing what you should try, but it will always works, but it's quite hard to implement actually. So the previous two control approaches were much simpler. Okay, and the main thing is that there is a actuated part and passive part, let's say, and depending on the task of the robot, there is some part of the motion which can be simply controlled by the feedback linearization or inverse dynamics control approach, and there will be another part which cannot be directly controlled, and usually we call it zero dynamics. So again, let's go back to the example. So if I have this model or simple robot, and it's important that the position of the x position of the cart is controlled, then this is the part which can be feedback linearized, so I can control it very accurately if I want. But the swinging motion of this pole will represent the zero dynamics, let's say, so we don't have direct effect on this, and my whole control system will be stable if the zero dynamics is stable in itself. So this is in a nutshell the idea of partial feedback linearization, and it involves Lie derivatives and everything else. So if you are interested in this, there's a very nice book in nonlinear controllers are summarized, and there's a paper in which the idea is applied for mechanical systems. So these are, I think, the starting things to read. So let's see some applications. As we have seen, we applied this whole thing to this cable hanging robot, in which there is the swinging unit, and now I zoomed the swinging unit just to show the problem. So at the original design, there were two huge fan actuators, so it can generate a thrust force, and the other is also able to generate a thrust force. So all in all, because this is a pair of forces, we can exert a torque about the vertical axis, and also we are able to exert a force. So these are two independent control inputs. but nothing else. And this is an animation which shows the problem. So if the center point of this swinging unit has to follow a desired point in space, then we always have to turn the swinging unit in order to have the thrust force in the correct direction. So you see that the beginning of each edge of this rectangular shape, you have to accelerate, so you have to rotate in the acceleration direction, but at the end you have to brake, you have to slow down. So you have to rotate back in order to generate some braking force. So it's quite tricky to tune the parameters and everything to work in a correct manner. This is a video for the same robot. It was done, this video was done during the COVID pandemic, so it was carried out at home of a PhD student in our department. Here, this is a modified design, so there are ducted fan actuators, there are 6 actuators, okay, so this is it. So there are 6 actuators, so they can have much higher number of control inputs, but still the system is underactuated, and you see that it was able to follow the trajectory. I don't want to show it again. Okay, and there are some problems with articulated vehicles, so it's enough from cable tethered robots or crane-like robots. So articulated vehicles are problematic when they are going backwards. So if you want to use a reverse, it can be a problem. And there, I don't know if you know this video. It was almost 10 years ago or something like that when it was a very big kick, and Volvo released this video to show how efficient their control is.
I've had my ups and downs.
Okay, so this was the video. So you feel that it is not a very easy task to reversing with this kind of vehicle. And we can also count that this is really underactuated. So there are three rigid parts of the vehicle here, for example. Here there is only 2 actually. But you can have just 2 control actions, the steering wheel and the gas pedal, and that's it. So it's definitely underactuated. Actually, the problem is that there are some also kinematic constraints here. So it's if you have a car, it's not 3 degrees of freedom in the plane, it's just 2.5. And this is again another problem. So there are half degrees of freedoms in rolling vehicles, but still you can say it is a very similar thing to underactuation. And they were very proud that they could put together a controller with which you can stably reversing with the vehicle. But if you were very focusing on the video, you can realize that only this vehicle is an articulated vehicle, and the other vehicle, which were doing a shift on its track, it is not an articulated vehicle. It's a normal one rigid body truck or lorry. Okay, so this was the funny in the video. So the articulated vehicle just followed a straight line, and only the other one could carry out this kind of steering motion. So it's another interesting application. And there is a big field of underactive systems which is related to legged locomotion. And this is a very nice video, which is not related to robotics, but some people realize that if they let a ladder freely move down on a slope, then it will provide a motion which is very, very similar to some animal or a human. So it's just doing some steps without any control action, obviously. It's a speed up at the end. But this is the main idea behind some walking and running robots. So they don't have too much actuators. However, they can copy or they can imitate the motion of a walking human. For example, this is our simulation in MATLAB. So it's just put together two rigid rods. There is a frictionless joint up here, and on the ground they can touch the ground and it can walk. But actually, it's not shown in the slide, but the gravitational force vector is a little bit tilted, so it basically walks down on a slope, and the slope provides always some energy while it's walking down. Maybe this video is a little bit better. So it was carried out by a student in the student hostel, and it was very, very hard to find the correct initial conditions with which this very simple structure could walk down on this slope. So the slope is very important, and the other important thing is that it does really matter how you start the motion, otherwise it cannot walk down. And it's also very important that there is no any computer or measurement or actuator. It is just two pieces of metal by a screw. And it was very hard to find the initial conditions, so that's why they were already drinking one glass of wine because it was a real problem to make this video. And this whole thing is also possible for robots with knee. So it's again a simulation. There is no any actuation, only the fixing of the knees in some time instances, but there is no active actuation on the system. And there is a video which shows something similar. It's not our video, it's actually a very famous video. So if you try YouTube the passive walker, then you will find this video very soon. And this is a simulation of some hopping system. So again, this is for the imitation of human hopping motion. And of course, in the airborne phase, it's totally underactuated. So if you deal with walking or legged robots, underactuation always comes into the picture. And this is again another very famous video. I guess everybody knows this, the big dogs. So they have to deal with similar problems. And there are some very important papers in this field. Actually, they are quite old, but this is the starting point again to read. And then, of course, you will find some newer papers that these are the papers where you can find the idea. And since then, a lot of different kind of walking robots were tested and built. So to go to the conclusion, so at the first half, we were talking about some basic concepts in robot modeling and control, but they were about conventional robots. But if you go to a robotic company, this knowledge is enough for a lot of things. And of course, there are some more special robots like underactuated robots. And it takes a lot of time to get know or learn everything about. It's not possible to learn everything about underactuated robots, but you can read a lot. So thank you.